Welcome everybody. This is Bart Vermang from the University of Uppsala, and he's going to be talking about aluminium passivation. Aluminium oxide passivation. So I've known Bart from his time at IMEC, which is where he did his PhD, and he's also done his master's in Belgium and at the Norwegian University of Science and Technology. So welcome, Bart.
Thank you, Nathan. So welcome everyone. So I have two topics today. First I will start to talk about silicon surface passivation, and then I will talk about CIGS surface passivation. So the first part is indeed my work that I did at IMEC as my PhD. It's mainly my PhD plus a few other results. So this will be about atomic layer deposition of aluminum oxides being used to passivate the rear of P-type pearl or N-type PERT. So this is UNSW. I'm not going to explain what pearl or PERT or PERC is. I think that should be quite clear over here. And then the second part, so recently, my last 2 years, I was a postdoc at the University of Uppsala, where I have been trying to implement something very similar. So an aluminum oxide passivation layer at the rear, between the molybdenum rear contact and the CIGS absorber layer, having openings as well. In this case, we're talking about nano-sized openings. In the last case, we were talking about micron-sized openings, of course. So first, IMEC. So IMEC is located near Leuven, and this is a nice picture of the old market of Leuven, which Nitin knows very well, probably. So this is the place where students go out and drink beers, Belgian beers. IMEC stands for the Inter-University Microelectronics Center, and also a picture or a map where you can see that Belgium is between the Netherlands, the UK, France, and Germany. So those are the 4 languages that we speak typically. IMEC itself is it's typically a CMOS-oriented research center. So they have a 200 millimeter clean room and a 300 millimeter clean room, which is being converted to 450 millimeter these days. But as well, they have a silicon PV pilot line. So very similar to the line I've seen today, but it's full with machines in IMEC. Some other state-of-the-art laboratories, for wireless, biomedical research, and all this kind of new interesting topics. So you see, the big part that's being done at IMEC is core CMOS, so which is IT components. All the others around it has been evolved from the CMOS, where they're using technologies from CMOS in other topics. So the same thing you also see in PV. They have all kind of PV, I mean. So silicon PV, organics, thin films, which is for the moment is mainly CZTS and amorphous silicon. But they also started perovskites, of course, because it's quite hot. They have been doing multi-junctions in the past, and they will be doing tandem cells in the future. Perovskites, CZTS plus silicon, typical topics. So this is my first part. So I'm just going to explain or remind you why aluminum oxide is such a hot topic for silicon surface passivation. There's a reason why IMEC has chosen Spatial ALD, which I also will discuss shortly. And then I have chosen a few topics to briefly discuss. So thermal stability, some results at pearl level, something which is called elimination independency, another advantage of aluminum oxide passivation of P-type silicon, and some PERT results and future things that we are working on, or that IMEC is working on. So why aluminum oxide? Aluminum oxide for P-type silicon has something which is called chemical passivation and field effect passivation. So chemical passivation, it passivates the interface very well. So it's kind of lattice matching. So it will lead to low interface trap density on top of silicon. Field effect passivation, aluminum oxide is one of the only known materials that if you deposit it on silicon, it has a negative charge density, which is also beneficial. So for example, you see the formula over there, which is a Shockley-Reed-Hall recombination formula. Thanks to the chemical passivation, the IT will be low. Thanks to the field effect passivation, the minority charge carriers will be low in the case of P-type. But there will be electrons, so the NS at the surface will be low. So here, for example, you see rear surface reclamation velocity as a function of corona charge density. So this is a charge applied on top of the passivation layer. And you see, where you have a negative corona charge density, we have amorphous silicon nitride, silicon nitride and silicon oxide. Where you have a positive corona charge density, we have aluminum oxide. which means in the aluminum oxide there is most probably a negative charge density. You see as well the surface accumulation velocity is very low for aluminum oxide. It can be low for silicon oxide as well. They just probably used here a low quality silicon oxide. But negative charge density, that's an advantage of aluminum oxide. Spatial ALD aluminum oxide. So we have been focused at IMEC at ALD. Atomic layer deposition. Why? Because Solitech and Levitech, the two manufacturers of spatial ALD tools, are located in the Netherlands. So there's a clear reason for that. So spatial ALD, the advantage is if you have temporal ALD, so the normal ALD, you have a chamber, and you will just pulse and purge gases into the chamber, and they will be deposited layer by layer on top of your surface, your silicon surface. In the case of spatial ALD, they're using space. So they just have slots of water and TMA, 3-methyl aluminum, next to each other, and then they just levitate the wafer through the different slots. In the same way, you will deposit ALD aluminum oxide in the end. The advantages are you can do it in line, you will have one-side deposition, you can choose the top side or the bottom side, and you can do it really, really fast. It depends in principle on how fast your wafer will move. Of course, there will be some limitations. But that's the reason we have been focused on ALD, not PCVD or something else. So the first topic I would like briefly discuss is thermal stability. One of the things that happens with ALD aluminum oxide and as well with PCVD or plasma enhanced ALD, but at different temperatures and in different circumstances, is if you have an ALD aluminum oxide layer and it's quite thick, it's more than 10 nanometer, or it has been kept with silicon nitride or silicon oxide, if you then bring it at a higher temperature, you might have something which is called blistering. So there might be bubbles in your aluminum oxide layers, which is not really beneficial, because in the end we are using ALD layers or aluminum oxide layers as a passivation layer, so they're always kept with metal layers. And in PERC or PEARL, typically we're still using co-firing processes. So if we bring it at a very high temperature later, you might create extra local contacts. And extra local contacts also means less passivation. It means more contacting, but you lose part of your passivation. So blistering, because of that reason, blistering is a not so good thing that happens, and in ALD it happens earlier or easier, because ALD is typically deposited at a low temperature. It's 300 degrees, 250 or 200 degrees even in silicon, in the silicon PERC case. So at a lower temperature, first of all, and there's no plasma involved. If there's a plasma involved, your layer is typically a bit more dense as well, which also prevents blistering at lower temperatures. What is blistering? We have been investigating this. And the end is a combination of stress and outgassing. So the left picture you have here is stress as a function of annealing temperature for a quite thick aluminum oxide layer on top of silicon. And what you see, so it's a cycling from 50 degrees to 400 degrees and back to 50 degrees. And in the meanwhile, you brought some tensile stress into your aluminum oxide layer. And it happens at the moment blistering starts. On the right side, you have outgassing, or you have a mass spectrometer. We used a mass spectrometer to measure a few gases coming out of the aluminum oxide layer during annealing. And there you see water and H2 as for different thicknesses, 5 nanometer or 30 nanometer, and different cleanings. So hydrophobic or hydrophilic cleaning before you grow the aluminum oxide layer. But more importantly, what you see is that a lot of hydrogen in the form of water or H2 is coming out of your aluminum oxide layer. And it stops at the moment you make blisters. So these two are related to the formation of blisters. So what you could do is to prevent blistering is just using thin layers, because then the gas will be able to go through your aluminum oxide layer, and do some annealing before you start to cap it or before you start to some high temperature processing. This way also you can prevent, or you can get some hydrogen, water out of your layer before it can make blisters. It's logical that you have some H2 and H2O, because in the end, TMA and water were the precursors being used to deposit the ALD aluminum oxide. So it's just some leftovers from the TMA and the water that are still within the aluminum oxide layer. So what we did is we are using spatial ALD aluminum oxide, a thin layer like I said, typically less than 10 nanometer. We do anneal it, and we use then a silicon nitride layer on top of it to have more reflection from the rear side. So rear internal reflection. In the meanwhile, at IMEC, Best large area cells are typically around 20.5%. Decent VOC, JSC, and fill factor. However, I put a few names over there, so similar technologies have been developed in industry as well. So Trina, Suntech, Canadian Solar have been working on similar technologies, reaching similar efficiencies or having the same kind of amount of success. So IMEC has changed to N-type, just because the rest can do the same thing, do something new. Another thing that's an advantage for aluminum oxide passivated P-type cells is illumination dependency or independency. So if you look at the VOC, VOC is related to shock-radiatal recombination, and depending if you have a positively charged or negatively charged surface passivation layer, your VOC will or will not become illumination independent or dependent. If it's positively charged, your VOC will be illumination dependent. Same thing for the JSC. If you have a positively charged layer, you will create an inversion layer and not an accumulation layer at the interface. So which means if there are some shunts, like you can see 2 shunts in the cross-section over here, you will lose electrons, even for JSC. So you will lose some of your current. It will also be illumination dependent. And we've tried to measure this, or we measured this by using filters for silicon oxide or aluminum oxide rear-passivated silicon Perix cells. And here you see the difference between aluminum oxide rear-passivated and silicon oxide rear-passivated as a function of illumination level. And you see VOC, GOC, and cell efficiency. And the degradation or the difference is really within the silicon oxide rear-passivated. So there you see a quite large illumination dependency due to a loss in JSC and VOC at lower illumination. That's also an advantage of having aluminum oxide as a passivation layer on P-type silicon. And we even made a calculation for lower solar irradiation regions, like for example Belgium. And on a yearly basis, you can lose up to 0.5%. So your average efficiency is not 19.5 or 20.5 anymore, but your average efficiency becomes 19 or 20. So you lose up to 0.5% for your cell. I didn't mention it, so typically for this part I will really go not in detail, but I always put the papers at the bottom of the slides so you can have a more detailed look. And I can also share the PDF after the presentation so you can have a more detailed look as well. So in the meanwhile, IMEC started to work on N-type PERT. In the end, they're using a very similar passivation stack. So N-type PERT is just, you have a totally diffused layer at the rear, which is now a P+ layer. So it's a bit more highly doped. However, they're using the same passivation layer, and they're really reaching high efficiencies. So the best efficiency for the moment is 21.5%. Again, a large area, decent VOC and other characteristics. Other things they are working on is, for example, you can use ALD aluminum oxide as a source for doping. So if you laser ablate, if you open by laser pulses the aluminum oxide, some of the aluminum will diffuse into the silicon and will give you a locally doped aluminum or a locally aluminum diffused contact. So that's something they have been working on. And also the P+ laser ablation and a contact passivation, of course. The other thing is, so we have been passivating in between contacts for a long time, but now, especially with ALD, you can deposit very thin layers. So you can make a kind of tunneling layer in between a metal contact and your silicon. So you can even start to passivate your interface at the metal contact. And that's something else that they have been working on and getting decent results. What I've been showing you is partly my PhD, but of course a whole team is involved. So I have to acknowledge all my team members and my promoter, which is Jeff Boortmans. So I took a nice picture of Jeff. So the more detailed part will be about my work that I did at Uppsala in Sweden. So this is a nice picture of the center of Uppsala, which is a very small city, comparable to Leuven in the end. It's a student city, and it's very cozy, as you can see. My work I've been doing is at the Ångström Solar Center. This is now Sweden, so we are more north compared to Belgium, and you have Norway and Finland around it, and it's in the middle of Sweden. So Stockholm is not shown here, but 1 centimeter from here, a bit lower than Uppsala, you have Stockholm. So Uppsala is 80 k north of Stockholm. It's not that cold in the end, according to me. So my work there I've been doing at the thin film solar cells group. So they're working on CZTS and on CIGS. So copper, zinc, tin, disulfide, deselenide, or tetra in principle. And then copper, indium, gallium, disulfide, deselenide. Within the Department of Solid State Electronics, and that's our lab, or that's our building where we are working and doing our experiments. I know I have a quite strong accent in English. However, everyone is making mistakes in their non-native languages. So for example here, so you have nanometers, and 0.1 nanometer is 1 ångström. So it's not angstrom or whatever, it's ångström. It's just something I want to teach you. Try to remember it. Because now we have nanotechnology, maybe in the future we might have ångström technology. So the Ångström Solar Center, why did I go over there? Because they have everything to make cells and to analyze and characterize them. So here you have a typical cross-section of a CIGS cell. So you start with a substrate, which is typically soda lime glass. You deposit a molybdenum back contact. It's still the best contact and being used in industry as well. Then you have the CIGS absorber layer on top of it, 2 to 3 micron, a buffer layer, typically still cadmium sulfide. However, you have zinc oxysulfide, you have a few cadmium-free alternatives in the meanwhile. And then the front contact, first an intrinsic zinc oxide layer, and then an aluminum-doped zinc oxide layer as a front contact, and still some grids and whatever. So all these layers we have in Uppsala. And even then CZTS or some cadmium-free buffer layers and so on. We can make cells, we can make modules, and we can characterize them. These are the goals that we have in Ångström. So we would like to, so last week on the EU PV-SEC there was an announcement by HSW that they reached 21.7% efficiency on CIGS. That's a top record efficiency. However, as an ex-silicon person, it's only 0.5 square centimeter. So what does it really mean? I don't know. As well, they're always comparing it to multicrystalline, and the best multicrystalline is 20.4, also 0.5 square centimeter, but no one is still, except in industry, no research labs are still optimizing multicrystalline silicon solar cells, so they shouldn't compare in my opinion, but still. Anyway, we want to reach 22 as soon as possible, or more than 20 for the cadmium-free, and for the CZS more than 12%. And the topics that we are focusing on is back contact passivation. So that will be the next slides. Of course, we need to do some electrical modeling to understand more what's going on. The absorber layer is very important in thin film cells, in this kind of thin film cells. They have been focused on the absorber layer for years and years right now to try to optimize it. That's the reason they have not focused yet on all the other layers or all the other interfaces. And of course, since we are in Sweden, we are doing some model energy yield modeling for the northern climate. Our spin-off is SolarBro, which is in the meanwhile daughter company of Henergy, which is Chinese. It was in the past Q cells. They're still making solar cells or modules. And in principle, they have the official world record because they have a 1 square centimeter CIGS solar cell efficiency of 21%. So this is my outline. First, I will have a look at standard CIGS solar cells. And then I will try to explain where this rear-passivation layer comes in and how it compares to silicon solar cells. Also here we're using aluminum oxides. A few reasons. One I can already say. I tried a few other layers before, but what we do here, we grow the CIGS layer on top of the aluminum oxide layer, or on top of the passivation layer. If you use a layer that is not that rigid, you just lose it. It is in a selenium atmosphere, so it's quite harsh. So we have been using, for example, cadmium sulfide in the past, or zinc sulfide. We just lost those layers. Then I will show you some results of the aluminum oxide rear-passivated CIGS solar cells. Interior, again, I'm going to compare to silicon because you see similar things happening, which is a good indication that the passivation approach works. Here, the challenge is to make nano-sized contacts compared to the micron-sized contacts in silicon. So we have, in the meanwhile, 3 different contacting approaches. I'm going to discuss those. And then the last topic is the soda lime glass we use is because of the sodium. Sodium is a positive thing for CIGS absorber layers. It improves them. It's a big debate what really the reason is. However, you just need sodium. So if you have an aluminum oxide layer in between the soda lime glass and the CIGS layer, of course you're going to block the sodium partly. So we have been doing some optimization. So at the left here you see a standard CIGS solar cell. That's a picture of NREL. So the molybdenum, or only the absorber layer with the rear contact. What they typically do in CIGS, they use gallium to grade the CIGS, to create back surface fields, very similar as you have it in silicon. So by gallium grading, they create also a back surface field at the rear, and they can reach surface combination velocities somewhere between 10,000 and 1 million centimeter per second. Very similar to a typical standard aluminum back surface field silicon solar cell. Same thing, the moly is not that reflective. It's even quite poorly reflective. Very similar to a normal full aluminum back surface field solar cell in silicon. What they did in silicon, of course, is, and you know, they have been making Perix cells, and at the rear, what does it mean? You have a passivation layer, you have the openings. The passivation layer will passivate, so you can thin down the layer, the wafer. At the same moment, it will reflect. Another reason why you can thin down the wafer, so you can have ever thinner wafer thicknesses in this case. So that's what we have been doing. So here again, you have the CIGS layer and the molybdenum layer, and in between you have the aluminum oxide passivation layer, and you can see already some local point contacts of around 200 to 300 nanometer. So the project I was doing for the last 2 years was called Perix. So you see it's Perc plus CIGS, but you also see that PIGS, so the PIGs are capitals. It's an European project, so I'm just referring to the 4 European countries that in 2011, and some of them still had a lot of financial troubles. And in my opinion, of course, solar or at least renewable energy could help them. And in the end, we got the funding, so maybe it helped, I don't know. So aluminum oxide has CIGS surface passivation. In the end, the main message is it's very similar, it acts in a very similar way as it acts as silicon surface passivation. So first of all, it can reach a low interface trap density, or you can reach a low interface trap density by growing an aluminum oxide layer on top of the CIGS absorber layer. So here you see some first principle calculations done by Sue, and he calculated that you can reduce the DIT within the whole band gap with around 35% by growing this aluminum oxide layer on top of it. I'm using here calculations because it's very difficult to measure it. CIGS is a great semiconductor for solar cells, but it's a crappy semiconductor in the end. So to really make measurements on CIGS, it's not that easy. As you can see in the next slide, so aluminum oxide also gives some negative field effect passivation, it seems, to the CIGS surface. So here you have CV measurements from metal oxide semiconductor devices. So the metal is aluminum in this case. The oxide is aluminum oxide, ALD aluminum oxide again, and the semiconductor is CIGS. If you do this on silicon, you get nice CV behavior. These are my best curves. You get worse than this. Anyway, you can see a few indications. In the left picture, we have two different thicknesses, 3 nanometer and 6 nanometer. And you can see the flat band voltage, so where you have the inversion or the depletion layer, or the depletion, it shifts to the right as a function of thickness, which is an indication that you have a negative charge within the aluminum oxide. Same thing in the right graph. There you go from as deposited to annealed ALD aluminum oxide passivation layers. Annealed is more honest. It's mimicking the solar cell process because we are growing the CIGS layer on top of the aluminum oxide, not vice versa. You see the same thing again. You see a shift in flat band voltage from the left to the right, or to more positive voltage, which indicates again a negative charge density within the aluminum oxide. And also the slope becomes less steep, which indicates that the interface trap density is even improved after annealing, which might indeed be the case. But as you can also see, these are not nice CV curves, so it's very difficult to quantify the DIT. So we have some DLTS measurements and this kind of things. We start to have some ideas, but to be conclusive, I'm still waiting a bit. However, we have been making cells using the aluminum oxide passivation layers. And if we plot now VOC as a function of the absorber layer thickness for the rear-passivated cells in green and standard cells without the passivation layer in black. So it's the same idea as with Perc. If you go for thinner cells, you should start to see the effect of the passivation. And you see it. So you see an increase, or at least you can keep the same VOC for having a thick absorber layer as having a thin absorber layer by having a passivation layer, which is not the case if you have a standard cell without a passivation layer, because you bring this highly recombinative rear interface closer and closer to the space charge region, so you just lose a lot of electrons, or you lose a lot of passivation. You have a lot of recombination at the rear interface. So here, this is very parallel to what we have seen in silicon already for several decades. JSC, same thing. JSC as a function of CIGS thickness for a passivated one in green and an unpassivated one in black. And you see you have more JSC if you have the rear passivation layer. However, you still lose some if you compare to the thick cells. If you look at the IQE as a function of wavelength, for a very thin cell, a cell with only 400 nanometers of CIGS, where typically normally in industry is 2 to 3 micron, then you see for a thin cell unpassivated, which is the black curve, you lose a lot of collection everywhere. While if you have the passivation layer, you collect more because of rear reflection, which we have been calculating already for the aluminum oxide passivation layer and also measuring, but also because of the passivation. It's so thin that you feel everything within the absorber layer. Now the challenge was to make the openings, the nano-sized point openings. So we had to come up with a few innovative ways to still have it kind of industrial viable for the future, but still have 200 nanometer of openings. So typically, diffusion lengths in CIGS are 1 to 2 micron, let's say. 2 micron, very, very high efficiency cells or absorber layers, and then lower for lower quality layers. So what we were aiming for from the beginning, just taking the starting from what they have in silicon and adapting it to the kind of circumstances we have in CIGS, we were aiming for openings of 200, 300, 400 nanometer, and then pitch or distance between the openings of 1 to 2, 3 micron. So what we did is, in the first case, we used cadmium sulfide nanoparticles. So the normal chemical Bart deposition we use for making the buffer layers has one disadvantage. It makes nanoparticles in the bulk, and they are deposited, but we use them to our advantage. So if you first deposit on the molybdenum rear contact cadmium sulfide nanoparticles, then if you sputter or evaporate a passivation layer and remove the nanoparticles afterwards, you can make nice openings in the passivation layer, especially in the case of aluminum oxide, which is very strong, so you're not going to start to scratch it or whatever. Here you have a few pictures, top few pictures, where at the left you see those cadmium sulfide nanoparticles, and on the right you see the same layer after removal, or the same top view after removal of the nanoparticles, and you see some openings of around 220 nanometer. Those cells, the advantage is it worked fine. The disadvantage was you lose some fill factor, you lose a few percentages in fill factor, because in the end, yeah, it's random where you have the nanoparticles, so it's only sub-optimized contacting grids. The second approach we used was molybdenum nanoparticles, so conductive nanoparticles, so that we could leave them over there. One of the disadvantages here is, or why we chose molybdenum is, if you would use another metal, it might be it becomes fluid or liquid during CIGS growth, or you might even start to diffuse it into your CIGS layer. Plus, it needs a good contact, and we know at least molybdenum is being used as a contact, so molybdenum nanoparticles should also give a good contact. So what do we do here? We deposit molybdenum nanoparticles, sputter again an aluminum oxide layer, and you have some shadowing, of course, effect by the nanoparticles, which means on top of this we can start to grow the CIGS layer and start to make cells. That's what we did. So here you see a cross-section, you see the molybdenum nanoparticles, and it's very difficult to see in this SEM picture the thin passivation layer, but we also have STEM EDX pictures, and now you can see the passivation layer as well. So it's nicely covered on top and in between the nanoparticles. So there you're passivating. So you're using the molybdenum nanoparticles as point contacts. It's also being used as a reflection, so you can optimize the reflection a bit more. We have not been using it yet, so they're still quite large. These are nanoparticles of 100, 150 nanometers, so plasmonics or whatever we have not been doing yet. But it might be even an opportunity to get some plasmonic effects inside the CIGS absorber layer. The third one, so the last two were more like to have a proof of principle, to show, look, this can work, and to say what we are doing might be industrially viable in the long term. But we also need study devices. So we also have been using just electron beam lithography to make nicely controlled grids. And that's a perfect study device. So in this case, you deposit the passivation layer, you put some resist, you open the resist by E-beam lithography, you etch away the rest of the passivation layer, and you get a nice controlled grid. Like here, for example, an optical microscopy picture. Top view, these are openings of around 200 nanometer, which you can still see in optical microscopy pictures. A bit closer, again, SEM EDX, where you can see that the openings are quite nicely opened. And the advantage of this approach is that you control the grid very well. So you can say, I want 1.5 or 500 nanometer in between the nano openings, nano-sized openings, and the openings itself have to be this size. So you can really optimize things. And what we see now is that we get really, really high fill factors. We're getting fill factors up to 80%, which is very difficult in CIGS first of all, and which is even more difficult in very thin CIGS. Typically, if you reduce the thickness of the CIGS layer, you lose fill factor because it's this great of a material. But one of the disadvantages, like I mentioned in the beginning, is the aluminum oxide layer itself is a barrier for sodium diffusion from the substrate into the CIGS layer. So here you see a SEM picture with the cadmium sulfide layer, CIGS in the middle, and the aluminum oxide layer at the right. And then we measured the sodium content within the CIGS layer for 3 different moments. So in orange, kind of orange, we have it as deposited. And you see, we know at that moment we have sodium deficiency. We have very low fill factors. But we found a way by putting field effects or because we are using PID, we are using potential-induced degradation, that we can move sodium inside the CIGS layer and increases to the red curve. And if we change the polarity of the electric field, we take out the sodium again, and only the sodium that we want to be there remains, which is the green curve. And this way, we have been optimizing our rear-passivated cells. So if you look at our publications, the best cells, we use this kind of tricks. So this is a summary. So here you see pictures of all three different approaches I've been using to make rear-passivated CIGS solar cells, or using cadmium sulfide nanoparticles in approach 1, just putting nanoparticles, putting the passivation layer, removing the nanoparticles, and you get your openings. In approach 2, we used the molybdenum nanoparticles and just left them there, used them as point contacts. And approach 3 was the E-beam lithography to really make nicely controlled grids of openings to study what is ongoing, of course, still, to study this passivation layer behavior in CIGS solar cells. But in all 3 cases, we were able to increase VOC because of the passivation effect for very thin cells. We were, at the same moment, we were able to increase JSC because of the reflection of the passivation layer. And we were even able to increase fill factor a lot in the case of the well-controlled grids with E-beam lithography. So that was my last slide. Thank you for your attention. And I would like to thank all the people and other research groups that have been involved in the meanwhile in this project.
Thanks, Bart. That was a great talk. Does anybody have any questions?
So which approach achieved the highest efficiency?
The last one. So the E-beam lithography is something we just started. So it's INL who's helping us for the moment. They have like a quite good nanotechnology lab, and they are doing the openings. So we have made our first cells in June or July, and those are great cells. So it will be out quite soon in an IEEE Journal of Photovoltaics paper. It's a cell with a CIGS layer of 240 nanometer only by accident. I wanted to have it thicker, but yeah, E-beam evaporation is not perfect. You always have some issues. Anyway, those cells typically, if you look in literature, getting 8 or 9% efficiency is very difficult. Our best cells, all our cells were really good, and we got efficiencies of 12-13% for a very, very, very thin layer, and really high fill factors. If you look in literature, very thin CIGS absorber layers, the first thing you see is that you lose fill factor, a lot. That's the reason I think this approach might be interesting for CZS as well. The big problem, in my opinion, in CZS for the moment, at least to do research, is the fill factor. You always have JSC and VOC are limited as well for the moment, at least VOC definitely. But you always have a quite low fill factor as well, which makes it difficult to do things at device level and to try to understand what's going on at device level.
Go ahead.
Yeah. I also realize you have mentioned that use aluminum oxide to passivate the front surface of the CIGS, right?
No, the rear surface.
Only the rear surface.
On the rear surface for the moment.
Okay.
However, so we didn't try it yet, because of certain reasons. But there is a paper out in Applied Physics Letters where they have been using titanium oxide, ALD titanium oxide, as a tunneling layer, very, very thin, on CZS. I would say it's not conclusive yet, because they're using the same devices for the LTS measurements and for device measurements, so for cell results. And you see an increase in VOC. And for the same cell, you also see an improvement at the interface for the defects, for the DIT. But it's the same cell, so it's normal that you should see this.
Put titanium oxide between the cadmium sulfide and the CIGS.
That's what they did. And they put it very, very thin. It's like just a few cycles.
So they're kind of tunneling between.
Yeah.
Oh, okay.
So that's something you could try. I've been trying it already on CIGS layers, but I made them too thick. And in the meanwhile, I had to do something else. So it's, yeah.
Thanks for the nice talk. With the aluminium oxide and the effect with sodium ions on PID, so I think the understanding is that the negative charge in the aluminium oxide is largely drawing the sodium ions to the interface, correct?
Good. No, thank you for the question. I didn't explain it in detail, I know, because the paper is just out and it's quite complicated and we don't understand completely what's going on. But what we do, we don't use aluminum oxide as a field. What we do is we put a cathode and an anode at the molybdenum we put an electric field between the rear of the glass and at the moly. So there's a field. And then by diffusion, we get the sodium, that's what we think at least. By diffusion, the sodium is starting to move through the openings of the aluminum oxide. But we don't know if it's really diffusion or whatever. But we see the sodium increases by having an electrical field between the rear of the glass and the molybdenum contact.
So the sodium is coming from the glass through the molybdenum into the aluminum oxide?
Yes. Not into the aluminum oxide, into the CIGS layer. Sodium, we want the sodium in the CIGS, in the CIGS layer. The main reason they always say is, it's a debate, but it has to do with the dopants. The more sodium you have, the higher your doping can be in the CIGS layer, the more efficiency you can create. So you have too low doping if you don't have enough sodium. But that's a debate.
So having that much sodium at the interface of the aluminum oxide, does that cause a problem for the passivation?
No, not in this case, because we also have it without. But the E-beam, we can control everything that well, and the openings as well, that we don't need to do this. We only do this for bad cells. So we also have good cells from the beginning. However, it's true you have more at the interface, because when you take it out, again, the aluminum oxide is blocking. It's a barrier. And we don't completely understand what's going there. But the passivation definitely is coming from the aluminum oxide only. It might have an impact from the sodium as well for the passivation, but aluminum oxide only works as well. This we are sure.
Because with crystalline silicon, there's one of the theories about why the cleaning is so important before you deposit your aluminum oxide is that if you do any pre-cleaning steps with sodium and potassium, that those ions stay at the surface and they get attracted. They stay at that interface because of the negative charge of the aluminum oxide, and that results in a very low DRT with crystalline silicon. So I look here and you've got quite high sodium concentrations right at that interface now.
Yes, but these are quite normal concentrations in CIGS, it seems. But it's true, it's a good idea. I have to check it again. I remember from my aluminum oxide silicon time, I remember indeed those papers. So it's something I didn't think about yet. It's true. But we are 100% sure passivation comes from the aluminum oxide. But it might be, like you say, that somehow the sodium is involved as well for an extra amount of passivation, an extra...
Or we might degrade it too.
Let's see. I don't know. Thank you.
Dave, did you have a question?
I was just going to ask, with your e-beam ones, what kind of area are you doing?
These are 0.5 square centimeter cells that we are making, but it takes a lot of time. So we are doing 12 cells on 2.5 by 5 square centimeter. And if I'm not wrong, typically it takes 7 to 8 hours. The good thing is, you can see it here somehow, we are using high power e-beam, high current. We don't care about how the opening looks. It doesn't have to be a nice square or whatever. We just want it to be open. So there we go fast.
Have you tried the alumina rear-passivation at the CZTS source?
CZTS, not yet. I'm working on it. Not right now, but it's something I want to try, yes. It's highly debatable for the moment as well, where we are losing everything in CZTS. Is it the bulk? Is it the interfaces? Mitzi thinks it's the bulk. Other people think it's the interfaces, but at least you see a lot of things happening at the rear interface that is not that positive.
Because diffusion is of the CZTS much shorter than
Yes, but they are also using typically quite thin layers, and maybe you can thin down the layers, and you could play with a few things. But I don't know. We're trying this.
The
It would.
thing is, if you see nano-layer, you probably will see more significant effect from
That's definitely the first thing we always do. Indeed, we're using this as a kind of device to see effects. Indeed. Want to say something? Yeah. We are trying it. Let's see. It's something we definitely want to, because in the end, that's what I want to say. So the Perix, the EU project, the way we sold it was saying, this might be interesting for alt-in film technologies. And that's something we would still like to prove now as well.
Is there molybdenum selenide layer from between CIGS and molybdenum?
In the point context, we definitely still have molybdenum selenide interfaces, which you need for good contacting. However, you can't see it on SEM pictures or whatever because we're doing co-evaporation. It's quite thin. If you do sputtering at high temperature, then you always see this very. So you can't see it very well here. I'm 100% sure because of the high fill factors. We would not have high fill factors. We have fill factors up to 81%. You would not have this if you don't have molybdenum selenide at the interface. That's my opinion.
Is there another question? Well, actually, I had another question. So, what sort of coverage areas did the three approaches have?
Thanks for the question. Good question again. So that's what we did. We scaled it from the silicon part to the CIGS part, taking into account diffusion lengths and all these kind of things. So we have the same area. It's somewhere between 2 and 5%. That's what we're aiming for all the time. So 2 to 5% of the rear surface is contacting area. And all the rest is passivated area. Or should be passivated area. We are making SEM pictures, STEM pictures as much as possible to really see what's going on and how it looks. And at least we see the openings, we see the passivation layer, so that's very positive. But of course, we are still looking at a very small area compared to the full area. But we're quite confident. For example, one of the things we did in the beginning was comparing, in the first paper, solar energy materials. We were still using 2 thin aluminum oxide layers, and we could not see them in SEM. And even in TEM, we had difficulties because, it was just one peak, just one measurement was the aluminum oxide layer, so it was not conclusive. So what we did there was, it was 2 to 4 nanometers of aluminum oxide. We compared cells with the full aluminum oxide passivation layers and cells with only the opening, the passivation layer and the openings. And you could clearly see the ones with the full layer were just extremely crappy cells, had a fill factor of 16%, fill factor of 16%, so 16%. So there, the blocking effect of the aluminum oxide layer was very, very clear. While for the cells with the openings, we got normal fill factors, higher VOCs, similar JSCs because it was a very thin layer, so no reflection. So that was the first moment we could somehow indicate, look at this passivation layer, we think it works. And then we got more and more results. So 2 to 5%.
So actually my follow-up question was, have you tried, not having any of these contacts to see if the sodium goes through? Or do you absolutely need, like, is it going through the aluminium oxide really, or is it mostly one contact?
It's the aluminum oxide. I'm thinking about it. I have a few reasons in mind, but I have to choose a good one. Oh yeah, the blistering maybe. Even for thin layers, we have seen the same effect of blistering of the aluminum oxide after depositing the CIGS layer on top of a full layer. It seems the sodium tries to get into the CIGS layer, but it didn't really work. And we got also a lot of blisters and this kind of things. We also have been measuring the sodium content in CIGS layers for full layers of aluminum oxide. Because in the beginning, I was really, to get to the first SEM and TEM pictures, having the passivation layer and the openings, that was really like a breakthrough because we could prove this is the cell, this is the way the cell looks. And it was very difficult because of the very thin aluminum oxide layer in the beginning. So that moment, I have been making complete devices without point contacts and very thick passivation layers, just because of reasons to make pictures that I could show the passivation layer. And then with those we have also been measuring where the sodium was and everything. And yes, it was a very good barrier layer for sodium. But it's even being used in other technologies for all kinds of barrier layers, aluminum oxide. It's even used in another thing, so CIGS solar cells. So indeed you use the sodium from the soda lime glass to optimize your CIGS layer. However, that's a very random process. So in industry, what they like to do is to have a barrier layer to block the sodium and put some sodium fluoride themselves. That they completely control the amount of sodium they put in the CIGS layer. And the best barrier layer they can use, they found out, is aluminum oxide, ALD aluminum oxide. For cost-effective reasons, they're typically using silicon oxide nitride, PCVD, but aluminum oxide, ALD aluminum oxide is much, much better. So that's maybe the best one.
Any other questions? All right, thanks, Bart. That was a great
Thank you.
talk.